So we are still on the Blitzer 5-5 notes. And we're still looking at solving trigonometric equations. And now the last three examples that we're going to do, this is part 2, are using identities to solve trig equations. So on number 6, what I notice right away is that my left-hand side, sine squared x minus sine x plus 1, is one trig function. And then on the opposite side, on the right, I've got cosine squared x. And I can't really solve like this with both the cosine squared and the sine squared. I can see how there's sine squared, sine, and a number, which makes me think factoring, but this cosine squared is not going to help. So my strategy here is going to be substitute using a Pythagorean identity so that I have just all sine or all cosine. So, and I can see where substituting for cosine squared is going to be easier, right? If I substitute for sine squared, I'm still going to have that sine in there. So I'm going to go ahead and substitute for cosine squared. And just as a reminder, it's cosine squared plus sine squared x equals 1. And then when I solve that for cosine squared, I'm going to have to subtract sine squared x on both sides. So cosine squared x equals 1 minus sine squared x. So that's going to be my substitution. I'm going to substitute the 1 minus sine squared x for the cosine squared x. So now I've got sine squared x minus sine x plus 1 equals 1 minus sine squared x. So I'm going to go ahead and add that sine squared x on both sides. So now I've got 2 sine squared x minus sine x. And then when I subtract 1 on both sides, the 1's just going to go away. It'd be a 0, so it's just going to be equal to 0. So now I can go ahead and factor again. Like on the last couple, we can use that strategy. So I could factor out a factor of sine x. And I'm left with 2 sine x minus 1 equals 0. And then we can go ahead and solve a zero product property. Either the sine of x equals 0 or 2 times the sine x minus 1 equals 0. And then we'll just go ahead and solve the second one for sine x. All right. So now I need to go ahead and draw some triangles. Well, on the 0, that means 0 over 1. So my y is 1, my r is 1, my x is going to be 1 also. So if I think, or negative 1, right? Like I'm not sure which it could be. So y is 0 right here, y is 0 right here. So we've got 0 or pi. So this is my 1, 0, negative 1, 0. Okay, and then for 1/2, I feel like we've done 1/2 a lot, at least in part 1 of the notes. A positive 1/2 could be in quadrant 1 or 2, and this would be a pi over 6 inside. And so our angle that goes around our terminal, our ray in standard position, or our angle in standard position for this one's going to be 5 pi over 6. So we have that x could equal 0. We have pi over 6 from this triangle right here, from that angle. And then we have 5 pi over 6, and then pi. So 4 answers on this one. So 7 is really similar. We're going to use an identity again, but this time they're not being multiplied or anything, nothing squared. And so one strategy that we can use is if I had an x squared or a y squared, then I could use a Pythagorean identity, but I don't have that. So I am going to force that to happen. I'm going to square both sides. Unfortunately, since we're squaring both sides, that introduces extraneous answers, possibly, right? We get extra solutions when we square. And so we need to check for extraneous on this one because we are squaring both sides. But we're going to do that so that we have a sine squared, we have a cosine squared, and we'll be able to do some Pythagorean substitutions. So I'm going to write out my beginning equation, sine x minus cosine x equals 1. And then I'm going to square the left, I'm going to square the right. When I square on the left, I'm going to get a sine squared x. My middle term will be sine x cosine x, but it'll be doubled. So minus 2 sine x cosine x, and then plus a cosine squared x equals 1. And now I know that identity is cosine squared plus sine squared equals 1. So I'm going to put them next to each other and reorder them. And now I can go ahead and substitute 1 in for these two using that Pythagorean identity. So I'm going to get 1 minus 2 sine x cosine x. There's a 1 on both sides, so we subtract it. So now we have minus 2 sine x cosine x equals 0. And then we can divide by negative 2, and we'll have sine x cosine x equals 0. And now, believe it or not, I can use zero product property. So either the sine of x equals 0 or the cosine of x equals 0. So it's like where I'm looking for where x equals 0 on the unit circle, where y equals 0. So if I think about all the spots for cosine x where this would be like 0 over 1, so anywhere my x is 0, that would be here and here. So either pi over 2 or 3 pi over 2. And remember, we're going to have to check all these answers because we're probably going to have a couple extra now. And then when my sine is 0, it's like y being 0. So y is 0 right here or here, at 0 or at pi. So now I want to go through and check those. So first I'm going to check 0, and we're checking in the original. So sine of 0 minus cosine of 0, does that equal 1? Well, my y value at 0 is 0. Wait a minute, y value at 0 is 0. My cosine here is 1. So I get 0 minus 1 equals 1, which is definitely not true. So I'm going to take 0 off my list of answers. It's not going to equal 0. And then I want to check, let's see, we'll check x equals pi over 2. So again, I go back to the beginning, and I'm going to have sine of pi over 2 minus cosine pi over 2. Does that equal 1? So my cosine of pi over 2 is 1, and my sine is 0, so 1 equals 1. So yep, it's going to equal pi over 2. I'm going to go over here, way over on the right, and check my other answers. So now we need to check x equals pi. So let's see, I'm going to have sine of pi minus cosine pi. Does that really equal 1? So sine of pi is 0. So remember, that's my y value here. I'm not up or down at all, so my y is 0. And my x is negative 1. So 0 minus negative 1. So this one's going to work. So x equals pi is going to be a solution. But what about 3 pi over 2? So sine 3 pi over 2 minus cosine 3 pi over 2. Does that equal 1? At least the equation we're checking it is pretty simple. So my sine of 3 pi over 2 would be a negative 1, and my cosine would be 0. And negative 1 does not equal 1, so this one's not going to be an answer again. So now let's see, I have x equals pi over 2 and pi. So again, because I squared both sides, we introduced extra solutions, so we needed to check for extraneous. So that's because we squared both sides, so be really careful on that. Our last one, sine x cosine x equals a negative 1/2. So our strategy on this one, this is maybe the most surprising one, is going to be to multiply by 2 on both sides. And if we multiply by 2, we can use a different trig identity. So we know our double angle, if we have sine 2 theta, that's going to equal 2 sine theta cosine theta. So we already have sine x cosine x. If I multiply both sides by 2, then I'll have 2 sine x cosine x, and then I can substitute that double angle in. And we'll have to solve a multiple angle problem again. So when I multiply both sides by 2, I have 2 sine x cosine x. And let's erase that because that's going to bug me. equals now -1 because we multiplied both sides by 2. And now I can go ahead and substitute. This is going to be sine of 2x now. So to write it as a double angle, I'm literally doubling the angle, equals -1. And so now I have something to work with. My sine is already isolated. I do have a multiple angle problem though, so I have to look for more answers. If this is -1/1, this is my y, this is my r. And so I'm looking at y is -1. This would be the only spot at 3 pi over 2. So we know that 2x is going to equal 3 pi over 2 plus multiples of the period. That's going to be 2 pi times n. And then I need to divide all of that by 2 to get x by itself, which is really like 1/2 times 3 pi over 2 plus 2 pi over 2 times n. So I'm really showing like every step here because I know this was confusing in class. So this is going to be 3 pi over 4 plus pi times n. So now I have to look for other answers. And we're looking on that interval from 0 to 2 pi again. So if I get to something bigger than 2 pi, then I stop. I don't have a solution. So first we're going to look at n equals 1. So that would be 3 pi over 4 plus pi times 1. So if I'm going to add pi, I need to write it as 4 pi over 4, which is 7 pi over 4. Okay, and then I need to go to n equals 2. 3 pi over 4 plus pi times 2, or 3 pi over 4 plus, wait, if I'm adding 2 pi, that's already going to be bigger than 2 pi. So this one's going to be too big. And so then I end up with x equals my first answer, that 3 pi over 4, and my second answer, 7 pi over 4. So because I had a 2x, it basically just doubled the number of answers I had. So now I've got 2. So this is the end of our Blitzer 5.5 notes finally. This is the end of part 2. You should be able to finish up the homework now.